I can't hear you.
You actually know what's going on with this major and how to teach it properly.
Well, you can't say
Thank
anything
you.
bad about any of you. You're testing quiz what we learned, not what we don't learn.
Everyone just tries to jam too much into a semester. You have to let it breathe so we can understand it.
Okay.
Already.
That's good to know.
It's a little example.
Now you're the only professor that talks with us.
Oh.
Yeah, the smaller classes.
I'm a talkative person, that's why.
True, small classes are nice.
That's right, smaller class. If you talk to Aerospace Lab 1 students.
I actually feel comfortable asking questions to these people.
No, I'm saying you should talk to Aerospace Lab 1 students. They don't talk to me at all.
You talk with me every now and then.
I talk to you.
You're the only one. Yeah, I mean, you. Most people are on their phones, are on their phones, so it is not really worth. Okay, let's continue what we started.
Have the exams been posted for?
No, I'm sorry. I really didn't have the time to go over this. Well, I was troubleshooting the problems with what's it called? Lab 1. It didn't help actually. So nothing serious happened. So we talked about the Rayleigh flow, right?
Mm-hmm.
We talked about the Rayleigh flow. This is Rayleigh, right? Is that the correct?
There's an I always. Is it EI?
That's Rayleghh. Is there an I there? I don't remember.
You spelled it last class, Reile.
Yeah, EI. I'm sorry. That's right. Rayleigh flow. Yeah. It's a very weird spelling. And the idea of the Rayleigh flow was that you can actually change the speed of a compressible flow with adding heat to it, right? So if you have a flow in a duct, if you apply heat flux to it, its speed is going to change. So you're going to have a Mach number, inlet Mach number, and an outlet Mach number. Yeah. Right? And so essentially there's a relationship between your temperature or your heat flux and let me see which equation we are looking at here. And also the Mach number. The changes in Mach number, this is the equation. Using the conservation equations, we can get to this equation. dm to dt, dm to m is going to be dt to 2t, 2 multiplied by temperature, multiplied by 1 plus gamma m squared, divided by 1 minus gamma m squared. So when you are heating this system, let's say you have a subsonic flow, and I know we discussed this, just we are doing this as a reminder, where m is smaller than 1, right? What can we say about this?
It's going to increase speed, right?
So when you heat up a system, when this is larger than 0, this is always positive, right? During supersonic case, subsonic case, this has to be positive as well. So if you heat up a subsonic flow, and this is a frictionless flow, the only thing that we have here is heating, you are going to get to sonic conditions. And of course, if you do the supersonic flow, it's going to act in reverse. Your Mach number is going to, I was supposed to use MA for Mach, but Mach number increases, Mach number decreases. And then what we did in the previous lecture is that we found a relationship between ds and dt, changes in entropy and changes in temperature. And this was the equation that we use, dt divided by t, right? If you plot this equation on a TS diagram, this is what you're going to get. Okay. So there is a T maximum value, and there is also a maximum entropy value. So this is S max, this is T max. Okay. And on this line, this is actually a line on which your M is going to be smaller than 1. It goes up and up and up until you get to the sonic condition, which happens at this, until you get to the maximum entropy, which happens at the sonic velocity, sonic Mach number, right? Here, we start on this bottom line, you have the supersonic inlet, right? So you start from a supersonic, let's say you start from this point, and this S and this T. You heat it up, you're going to move on this line, your M is going to increase until you get to the sonic conditions. How much heat do we need to get to the sonic condition? That is going to be the surface area under the curve, right? Or it's going to be TdS, okay? Or delta T multiplied by delta. And the reason we can do this is because this process is a reversible process, because there is no losses to friction, right?
Why is the sonic max as the temperature starts decreasing? Why is it not a top? Why is it not where the T max is?
So if you rewrite this equation, how can we find the maximum temperature using this equation? How can we find the maximum temperature? You can just move everything to one side, right? Take the derivative once more. If that derivative, find the location where that derivative is 0, and that is going to be equals to Mach number where it is a square root of 1 over gamma, which is smaller than 1. Let me just make sure I'm giving you the correct value. Yes, 1. If you do the calculations, it is a very easy calculation, right? But why does this happen? How can you explain this? That the maximum temperature doesn't happen at the sonic condition. There is another location where the maximum temperature happens. That's actually, at some point, what happens, you have to back up a little bit and try to explain what happens to your system when you are adding heat flux, when you're adding heat to it. What is happening to the system? You are increasing the total temperature of the system, right? And this total temperature, CPT, is equals to Cp multiplied by the static temperature, which is this temperature, plus V2 squared divided by 2. After this Mach number, what happens is most of the heat flux and also some of the energy, some of the static energy is going to go into increasing the speed, right? And that can be actually explained using a molecular dynamics, molecular analysis. But we are not going to go over that here, right? So this, instead of your heat, instead of this total temperature increasing both of them, it's not going to increase both of them. It's only going to increase this one. And also your static energy is going to help increase the velocity as well. So you will see an decrease in temperature, okay? Okay, so for your homework, you actually have to determine these two locations. This S max is where M equals to 1. And this temperature, what is the temperature at the sonic condition? It's the sonic temperature, right? How do we show this? T star. So for your homework, you're looking at these 2 points. But by looking at this plot, you can see that, well, let me ask you this. Let's say I have a subsonic flow coming in. I have heat flux or heat that is being applied here. Let me just use heat. And that heat is greater than the heat required to reach the sonic conditions at the outlet. Okay? So, subsonic flow. There's an inlet for the subsonic flow. What's going to happen is I'm going to apply a heat that is higher than your sonic heat required. What is going to happen? What do you think is going to happen to the outlet? By looking at this figure. I'm going to go one by one, right? Let's start with Zach.
What's gonna happen? I think once you get past the sonic, where it breaks the sound barrier, Mach 1, it'll actually start decreasing, and so it won't be as fast as it is.
So what you're saying is that when you get to this sonic condition, it will go back down, right? Okay. Next, Joseph, right?
Yes, sir. I honestly don't know.
Okay. Just think about it.
Well,
Just you can have any opinion.
We're adding more heat than is required for the process, right?
Is required for the sonic outlet.
Then wouldn't the temperature increase? I mean, that's the only guess I have. It's really simple.
Okay, so what Joseph is saying is that your temperature is going to increase. So we're going to move in this direction. So M is going to be greater than 1, right? Let's go to, I forgot your name. What was your name? Yeah, I forgot yours.
Steven,
Steven, yeah, I'm sorry.
would the flow start to break apart?
What does that mean?
Like, so I'm assuming the flow is like going in laminar, would it become like more turbulent because it's like it's bouncing back and forth within that region?
That laminar to turbulent flow analysis doesn't really apply here because we are talking about the compressible. So your speeds are already very high, and it's a flow inside the dark where transition from laminar to turbulence happen at a very low Reynolds number, right? Okay, so that wouldn't happen. What was your name?
Patrick.
Patrick.
I think it would, because with subsonic, when you heat up, it goes closer to that sonic, like Mach 1. And then if it's more heat than that, it would go past it. But because when you add heat to supersonic, it would go back down. So it would like end up like buffering back and forth between, like, and trying to find equilibrium. So like Mach 1, I guess.
Okay. What was your name? Camden.
I was thinking kind of similar to what Patrick was saying, of like because as you, with like changing the temperature, it'll kind of like hit that equilibrium between at Mach 1 when you're like adding and decreasing heat.
So what you're saying is that, let's say we reach the Mach 1 here, right? We are gonna get 1.1, then it's gonna go back to 1.1. Is that what you're saying?
I guess. I'm not really sure. But
Okay. Is that what you were saying?
Well, it would hit like 0.9 the second time,
Yeah.
and then back up to 1. And then
yeah, that.
Okay.
I kind of agree with him. I feel like once it gets past that like added temperature, there will be like some sort of, I guess, like oscillation between the Mach numbers. But I feel like if you add like a higher heat flux, it'll like still shoot up and then get to the point of the graph where it'll like start decreasing in Mach number if you add more heat flux to it.
So you're gonna go to a maximum of 1, then it's going to decrease?
Because like on the graph, if you started, oh, are we starting less than 1?
We are starting with less than 1, yeah. Subsonic.
Well, I kind of agree with him with like how it'll like stall per se, like in between the ranges.
Okay.
I don't know, per se, how to do it.
Okay.
Like how so that would happen.
Okay.
I'm kind of agreeing with with Mach 1, because if it's coming in subsonic and you're heating it, then it's gonna increase in velocity, but like adding heat won't increase that velocity anymore past Mach 1. And like if it was reverse, it came in above Mach, then it would decrease it, but heating it won't decrease it any more than that.
Okay. John, right?
Yeah, I think it would, similar to what they were saying, except I don't think it would ever reach Mach 1. I think it would just like get closer and closer and closer, like I guess converging that way.
Okay.
I kind of agree with them, but the only thing that I want to add is I feel like it's going to pass the Mach number. But so as we heat it with constant heat, yeah, we're going to start in below 1. It's going to reach up to maybe past the 1. It's going to go down, but after that point, it'll never go down that Mach 1 because we're constantly heating it up. So you're going to find an equilibrium. It's going to be like you said.
Okay. So most of you, I guess, observed the correct phenomena that it is not gonna go higher than Mach 1, right? It is not possible. And that oscillation doesn't happen though, right? Why doesn't it happen? Look at the TS diagram. The idea is your delta S is either 0 or higher than 1, right? So you cannot go to a lower entropy value, right? Your delta S cannot be 0. That's unphysical. That doesn't happen, right? That's the second law, right? So this oscillation doesn't happen, right? And eventually, if you have reached, the idea here, and we have to move on this line, if you have reached a maximum value of entropy here, if you have reached the maximum value of entropy, then you cannot go lower than this, right? So what should happen? At your exit, you should get that maximum value. That's the idea, right? Because after the exit, that's this process of flow inside the dock is already done, right? You don't care about what happens afterwards. So your maximum entropy has to happen at the exit. But based on this plot, we cannot really jump in the same location. We cannot have Mach 1 and then Mach 1 and then Mach 1, right? As your flow is moving, your velocity has to change because you are heating it up, right? Either decrease or increase. So what will happen? Let's say your choking happens, or Mach 1 sonic conditions, which we call choking, right? I think we have talked about choking. Is it choking? I don't remember, is it with K or CK? CK. So choking, sonic condition. But let's say choking happens at a length that is smaller than your pipe's length, duct's length. What will happen? Right? That's the thing that we wanted to figure out. What will happen here is that your inlet condition is going to adjust itself, right? Since we are not in a supersonic condition, this presence of this choking happening, your inlet can see this obstacle here, right? So it's going to adjust itself to a lower Mach number, right? So the choking happens at the outlet.
Does that create a shock wave at the inlet?
No, because you are in the subsonic region, right?
Then how does the flow adjust?
That's a very, very good question. So your streamlines are going to surpass the pipe. Not all of them are going to go inside the pipe. And this phenomenon is going to be called a spillage. Your flow is going to spill around the duct, right?
So it's kind of like when an airfoil going subsonic, the flow sees it before it actually sees it.
That's the idea, but we are talking about the internal flow, right? That's external flow,
But
right?
if it sees it before you actually get to it.
Your inlet sees the choking condition, yeah. Right? So it's going to adjust itself to make sure that the choking happens at the outlet, right? And why do we want to have choking at the outlet? Because choking or the sonic conditions is synonymous with the maximum entropy, right? And we cannot have an entropy higher than the maximum entropy, and if you have already reached the maximum entropy, it cannot go lower, right? So that's what happened.
So the max Mach number that it can get into in any, I guess, an actual physical limit is Mach 1, and it will adjust itself no matter what.
The outlet Mach number, yeah.
So it can't, like in a duct, it is physically limited to Mach 1.
If it reaches the choking condition, yes.
And this is only a duct that has a constant cross section.
Yes. We are talking about the constant cross section, yeah. We have already talked about the convergent divergent nozzles, right? This is only a constant cross section and also a frictionless duct. So your friction has to be negligible compared to the heat transfer. Okay. Well, what if the flow is supersonic? What's going to happen? The same thing applies, right? We cannot go lower than maximum entropy, right? Let's say it is coming in. And your heat input is higher than the sonic heat, the choking heat. And the sonic heat flux required is actually the heat flux that is going to give you the choking condition at the outlet, right? Keep that in mind. Okay? So what if we have a supersonic flow?
Would it push the choking forward in the duct?
What do you mean by forward?
Like, because the inlet would adjust on subsonic to allow the choking to happen further back. So like with supersonic, it would choke faster, like push it forward in the duct then?
Then what is going to happen afterwards? Let's say the choking happens here, and your supersonic flow makes your choking to go back. What is going to happen afterwards?
Creates a vacuum.
Creates a vacuum. That's going to be paradoxical, right? Yeah, if you create a vacuum, then you have to increase you have a very low pressure here, zero pressure, and a very high pressure here. So it's going to increase the velocity. Again, you have to, whenever you're thinking about this, you have to go back to this theory, which is a correct theory, that the maximum entropy must happen at the outlet. And the maximum entropy happens during choking. So if your choking happens inside the pipe, based on the calculations, your flow has to adjust itself in some way to make sure the choking happens at the outlet. Okay, does this make sense? Okay. So for subsonic flow, the flow spillage happened, right? The adjustment happened that way. What can we do for supersonic flow?
If you have kind of like what you did at subsonic, have spillage where the whole flow doesn't go into it, only a portion of it, then I don't know, that's what it might have. It might go around and not go through it, it slows down.
So if your flow goes through, if the flow spillage happens for supersonic, your Mach number is going to decrease, meaning that your choking, supersonic choking, is going to happen earlier. Right? So the spillage is not going to help. But there is one more problem before this problem, right, with the spillage idea. The idea is you are in the supersonic condition, so that choking is not going to be seen by the outlet, right? Because we are, that obstacle is not going to be seen by the inlet. By the inlet, right? Does this make sense? Because we are in the supersonic condition, so an obstacle present is not going to be felt by the inlet, right? So what is going to happen? What is the only mechanism we have that is going to help us adjust the flow during a supersonic condition?
Expansion and compression waves.
Okay. What kind of a wave you are going to see here? Keep in mind that we are assuming this is one-dimensional flow, right? An expansion. So you want to see even higher velocities. Why do you want to see even higher velocities? Expansion wave where? An expansion wave really depends on your geometry. On a flat plate, you are not going to have an expansion wave. You need to have a normal shock wave. So the adjustment is going to happen with a normal shock wave, right? A strong normal shock wave. So at some point, you're going to get a normal shock wave, and then afterward, you're going to have a subsonic flow, right? And the choking is going to happen at the outlet, right? The only thing you need to determine here when you're dealing with this is the location of this normal shock wave. And that's going to be a problem that you need to solve, right? Okay, any questions here? No. We are going to have the same concept when it comes to fan flow. The difference is, instead of controlling the flow parameters with heat, we are going to control it with friction. So we have friction, right? And this friction is going to affect your flow velocity. Meaning that in your momentum equation, you are going to have another body force added. If you recall, in the momentum equation, we only had a pressure force. I'm pretty sure you don't recall this, but take it from me at face value, right? We only had a pressure force, right? Here, since we have friction, we need to add another force, which is the shear force at the wall, right? Friction force, right? If you put that in the momentum equation and try to solve it little by little, you are going to get to this equation. 4 multiplied by your wall friction coefficient multiplied by dx divided by hydraulic diameter 1 minus m squared divided by gamma m squared 1 plus gamma plus 1 dm squared divided by m squared. I think we know what all of these parameters are, maybe except for this value, dh. Who can tell me what dh is? Have you ever heard of this? Yes? Do you remember what it is? No. This is the hydraulic diameter, right?
Yeah, it's something with Reynolds number, right?
What's that?
Don't you use like Reynolds number and stuff?
We use this to calculate the Reynolds number inside a pipe, right? For a regular circular pipe, your hydraulic diameter is just your diameter. But let's say you have a rectangular, the cross section is rectangular, and what is the value for the diameter you want to use? It's going to be the hydraulic diameter. How do we calculate the hydraulic diameter? It's 4 multiplied by the area, that's the cross-sectional area, divided by the perimeter or the circumference. Right? Okay, so by looking at this, your hydraulic diameter is always positive, your friction coefficient is always positive, and as you go from inlet to outlet, your dx is going to be positive as well, right? Your dx is always positive, right? As you are moving, right? So, what is going to happen to subsonic flow? Flow inside the pipe with friction. Subsonic flow inside the pipe with friction. What is going?
Slow down.
It will. So subsonic flow will slow down. Yes? Look at this equation. Subsonic flow, this is always positive, right? dx is always positive. What needs to happen to the changes in the Mach number? this needs to be positive. So your Mach number is going to increase when you have friction.
Is it because like, are we going back to like flows, because if there's friction on that, it's just gonna have high pressure difference, which is gonna speed up the airflow, something like that.
Can you repeat what you said?
It's like, I'm probably wrong, but like if you have friction in the pipe, throughout the middle, our flow is gonna speed up because of the friction on the.
You're talking about the fully developed flow, right? The body layer merging to each other. Okay, which I don't think it has been discussed for this class. So, but let's actually, I don't know. Do we want to spend time to discuss this? Let's talk about the reason. If you're very interested, we can talk about it in the next lecture. Okay, but I want to finish this, and I want to solve some examples. Which means that for a supersonic flow, your Mach number is going to decrease, right? Okay. Everything else, everything is the same as the heat transfer inside, as the flow with heat transfer, right? You want to have your inlet at the choking condition if your length is higher than the choking length, right? So your flow has to adjust itself with either by a shock wave or by the flow spillage, right? And if you plot the TS diagram, I should give you the TS equation as well. So I have the TS equation here. Yes. So this is going to be the main relationship between entropy and temperature. dt divided by t. And we can derive this from the Gibbs equation for this specific case. Your TS diagram is going to look like this. You have subsonic, supersonic. For this specific case, your maximum temperature and maximum enthalpy actually happen at the same location, and that's the sonic condition. Okay? Any questions so far?
You said that point with the max temperature and max?
I'm sorry, max entropy, not max temperature. Max entropy. Okay. One more thing that I want to say, and then we'll go to solving examples. So, for the friction flow on a TS diagram, we have added one term to the momentum equation. Right? Conservation of mass and energy equation is similar to normal shock equations. For the flow with the heat, which I'm just going to superimpose just two random flows here. We are heating this up. So your momentum equation and conservation of energy, conservation of mass are the same as the normal shock equations. The only equation that is different is energy equation. We can argue that at these two specific locations, is m equals smaller than 1 and m larger than 1. And let me actually have to, if you do this, this has to look like, let me try to make sure that this is accurate enough. Something like this, right? Has to be like this. So this is your, one can argue, since these two equations are the same in the heat flow, in the heating, the Rayleigh flow is the same as normal shock wave equation, and these two equations in the funnel flow is the same as normal shock equations. At the cross section of these two flows, where these two lines, Rayleigh lines and the funnel lines, cross each other, one can argue that the three equations are actually at those specific points are going to give you the same exact results as the normal shock equations, right? Because they are essentially equal to each other, right? All three. Does this make sense? Okay. What does it mean? This means that if you have the Rayleigh line and the funnel line, or if you have the Rayleigh tables and the funnel tables, you can actually set them to equal to each other for specific cases and find the normal shock wave data. So this is going to be your before shock, upstream of the shock, and then after it reaches the shock wave, your flow is going to have these properties. Does this make sense? It will jump to the subsonic case. Does this make sense? This is the last thing that's part of the theory we wanted to discuss. But let's solve one example from the Rayleigh flow, and then we'll come back to discuss the harder funnel flow examples. And this is your book example. So if you have the book, you can look up this example in the book. Chapter 2. You don't know what chapter is this? That's. No, I mean this. I'm just kidding. Don't worry about it. So example 2.6 of the book, right? I'm going to write down the example, the text of the example for you here. So we have air that enters a constant area I guess I can show it in the book. That's going to be easier. That's page 74. Let me actually, I think I have the book here, right? Yeah. Let me show it on the book. So this is the problem. Air enters a constant area duct of circular cross section with diameter d equals to 20 centimeters, and it's the same as the hydraulic diameter because it's a circular duct, right? The inlet conditions are Mach number m equals to 0.2, and the total pressure is 100 kilopascals. Total temperature is 288 Kelvin. There is heat transfer to the fluid at the rate of 100 kilowatts. Assuming the flow is inviscid, that allows us to neglect the frictional drag force on the fluid, calculate the mass flow rate through the duct. Okay? And we also want to find a critical heat flux that would choke the duct for a given M1, right? We also want to find the exit Mach number, the percentage of total pressure loss, the entropy rise, the static pressure loss, and the last part G, it is not important. You have to keep in mind that R is 287 joules per kilogram Kelvin, and gamma is 1.4. Okay, so how can we solve this? Again, as it has been the case for the past couple of lectures, we want to look up the tables, right? This specific one is going to be the Rayleigh flow tables. Let's actually go to the tables here. So Rayleigh flow tables, what is the Mach number? Mach number is 0.2. So we are talking about this line. This, I mean, you can see that line, right? What can we read from this? We can read the static pressure ratio with the sonic pressure, right? P divided by sonic static pressure, T ratio of the static temperatures, densities, total temperatures, total pressures, and also the entropy rise, right? The rise in entropy. But all of this is for a choked outlet, right? For a sonic case. This is the ratio between your static case and the sonic case, right? We are asked to find the mass flow rate through the duct. Okay. So how can we find the mass flow rate through the duct? If you recall, we only had one equation that gave us the mass flow rate, right? And that actually, I think we talked about it 2-3 weeks ago. I'm going to write down this equation for you, but you should have it in your notes. The square root of gamma divided by R, PT1 divided by square root of total temperature 1 multiplied by the area multiplied by M1 multiplied by 1 plus gamma minus 1 divided by 2 M1 squared to the power gamma plus 1 divided by 2 gamma minus 1. This is all the power. And we already have everything we need here. Just plug in the values, you will get the mass flux. And the mass flux here is going to be equal to 2.525 kilograms per second.
That's raised to the power, right?
Yes, this is raised to the power. Only the denominator. Okay, so this is part A. Part B is asking us to find the critical heat flux that would choke the duct for a given M1. How can we find this? We are looking for Q star. I mean Q double prime star. It is asking for a heat flux.
Q dot over M dot. Q dot over M dot.
How would that give you the critical heat flux? Don't look at the solutions. Just give me your opinion. And that is wrong.
Is there something in the table?
We looked up the tables, right? This is the. Why does it always read? Yeah. So what value can you read from this table that can relate to your total heat?
Temperature ratio?
Total temperature ratio, right? So we have the total temperature ratio. Do we have the total temperature at the inlet? Yes. So we can find based on that, because we have the value, we can find the total temperature, critical total temperature for this specific flow, right? Based on that ratio, that's going to be TT star, right? TT star can be found. But how can we relate this to heat flux.
So,
How does total temperature relate to heat flux? Or total heat? Total heat is going to be essentially, to find the total heat, we have to find the enthalpy increase, right? How much total enthalpy has increased. What is the relationship between enthalpy and total temperature?
The total enthalpy of what?
Doesn't matter, in general. What is the relationship between total enthalpy and total temperature?
like CP.
CPT, that's it. CP, exactly. So CPDT, which is going to give you CPT at two different locations, right? TT1. So TTSR minus TT1. We have the TTSR, we have the TT1. The only thing we don't have is C of P. How can we calculate C of P? Which table? The what?
It's a shock.
The what is C of P? How can you find it from the shock table? Okay.
One of the tables I know exists.
What is the relationship between C of P and gamma and R? Do we have this relationship?
Maybe.
Gamma was CP divided by CV, right? And R was CP minus CV, right?
Yeah.
So yeah, if you play with those two equations, you will get to this equation. CP is equal to gamma divided by gamma minus 1 multiplied by R, right? And if you are given the values for these two, gamma is 1.4, R is 287. You plug in the values, is going to be giving you 1004 joules per kilogram Kelvin. So we have all of these numbers. You just plug them in, and it's going to give you the heat flux required to get to the choking condition for this specific Mach number. And it's going to give you 1,000, let me just write down the number. It's going to be 1,376.5 kilojoules. And what is the unit here?
Heat per kilogram per second?
Per kilogram second?
Kilojoules per kilogram second?
Why is this a second here?
Because it's a flux rate, isn't it?
So this is joules per kilogram Kelvin.
I guess just based
And flux is not per second, it's per square area, right? And this is something I think the author of this book wasn't I guess he was aware of this, but he didn't really notice. Heat flux is always heat per unit area, right? Yes.
I'm gonna ask my question after we done this one here.
Sure. And this is multiplied by K, so unit is going to be kilojoules per kilograms. Yes.
Wouldn't that be joules per kilogram?
If you plug in the numbers, you will get to kilojoules. Right? The correct unit is joules per kilogram. When you have kilojoules, this essentially means that your value is this multiplied by 10 to the power 3 joules per kilogram.
Yeah. My question, I know it's kind of stupid. How did you get the temperature values?
From the tables, right? So let's say we are given the TT1, right?
Okay.
And we are also given the Mach number, it's 0.2.
Is the temperature one total temperature? Because I thought the total temperature was the temperature plus the velocity divided by squared divided by.
That's correct. But you are given a value for total temperature. If you look at, I have it here. But on the example text, it says total temperature 1 is 288 Kelvin. So you are already given the total temperature. You don't need to worry about that calculation.
Then we use
Okay.
the ratio from the table to find star.
And then you go to the, exactly. And then you go to the table. you are given this ratio. You see here, this total temperature ratio. You have the ratio, you have one of the temperatures, you can find the other one. Okay?
Okay, so I was just confused as to whether or not the initial temperature was the total temperature or just the temperature.
No, in the text, all of the variables, the total pressure and total temperature is given to you. So you don't need to calculate them from the static ones. Okay? Yes?
And just to clarify, total temperature is the same as stagnation temperature, right?
That's right. In reality, that is not correct, right? But for our purposes, it is correct, right? Because we don't really care about the elevation change. We are assuming everything is one-dimensional, right? When you're assuming everything is one-dimensional, total and stagnation properties are the same, right? Okay? So there is no elevation change in the flow inside the jet. Okay, so we can find this heat flux, which is 1376.5 kilojoules per kilogram Kelvin, and we are given a heat rate. This is not a heat flux, it's just heat per unit mass, right? Just keep that in mind. We are given a heat rate which is 100 kilowatts. How can we determine whether we are reaching the choking condition or not? We have to compare these two heats, right? But one of them is a heat rate, the other one is a heat per unit mass. Okay? So how can I convert the heat rate to heat per unit mass, or the other way around?
So we have the mass flow rate.
We have the mass flow rate, right? Do you want to say something else?
Wouldn't you multiply the mass flow rate times the heat flux?
Exactly. So we can either multiply this by your mass flow rate, which is kilograms per second, which is going to be giving you joules per second or watts, right? Or we can divide this by mass flow. It doesn't really matter, right? And your book actually has divided the two. So it has divided this Q by m dot, right? And if you do this division, your Q, your heat per unit mass, is going to be equal to 39.61 kilojoules per kilogram. And this is the applied heat. Which one is bigger? Q star. Yeah, be confident. It's just comparing two numbers. So Q is smaller than the Q star. What does this mean for our pipe?
We don't put enough heat into it.
We are not putting enough heat into it. So although the velocity Mach number is increasing, we are not going to get to the choking condition because we don't have enough, we are not applying enough heat. Okay. So we are asked to find the exit Mach number. How can we find the exit Mach number?
Use the long equation.
Use the what? What do we need to have for the table? So in the tables, you either have the ratios of temperature, pressure, whatever, right? Or the entropy, or the Mach number. Which ones do we have? Temperature ratios. How do we have the ratio? So for the exit, let's say this is inlet 1, exit 2. And the idea is choking should happen. We are going to need to have more heat input, right? So choking doesn't happen here. We have this T star, right? We have this T of T star. We have the T of T. Well, how can we find this ratio?
We already know the inlet temperature, so can we? I don't want to do that again. We already know the inlet temperature, so.
We already know the inlet temperature. How does it relate to exit temperature? Exit total temperature.
I don't really know.
Think about it. How does your exit total temperature? You know the energy input, you already know how much energy you're putting into the system, right?
Energy conservation.
How can you calculate that? What is the manifestation of energy conservation here? So at one point you have the heat input, right? And also the enthalpy change between inlet and the outlet, right? So we have one enthalpy and another enthalpy, and then heat input all over, right? So your heat input has to be equal to HT2 minus HT1, right? What is HT2? How can we calculate HT2 based on the information we already have?
Can't leave the chart?
No, we don't have enthalpy charts here. We just did this, just like three minutes ago.
Like the CPDT.
CPT, right? Or CP delta T, right? So the TT2 minus CPTT1 is going to give you Q, right? For the sonic conditions, we put T star here and it gave us Q star. But for a non-sonic condition, we already have the Q for that non-sonic condition, which is going to be this 39 kilojoule. We have already calculated CP, we have the TT1, we can calculate the TT2, which is going to be equal to 327.4 Kelvin.
How did we get that T2?
We have this, and we have,
Q also, yeah, okay.
yeah, Q is your heat input, right? Is this 39. Is this clear?
What was the value?
The value is 327.4 kelvins. So we have the TT2. How can we use this TT2 to find the M2? Exit Mach number.
The Prandtl-Meyer. Because it's
Prandtl-Meyer equation is used for expansion waves.
yeah.
It is defined for expansion waves. We don't have an expansion wave here. It's just a Rayleigh flow.
Yeah.
Just think about it. Don't go over your notes. Think about it. Look at me. What's that?
The tables?
Yeah, the tables. Yeah. But what do we need?
We need the TT2 and TT1.
Need the ratio.
fraction.
We need the ratio, right? We need the ratio between temperature. But which two temperatures?
2 and 1.
Mm,
Yes, no.
a star and 2 in this case, right? Why? Because in your tables you have one total temperature, one a star total temperature. So if you calculate TT2 here on this one, right? If you calculate TT2 here and TT star, which is going to give you, what is the value? The value I have here for TT2 divided by TT star is going to be 0.1973. So 0.1973. 0.1. It is going to fall somewhere between these two values, right? Between 0.2 and 0.1. So your exit Mach number is between 0.22 and 0.2. For this one, you have to do an interpolation, right? Just keep that in mind. I hope you have done this for the exam as well. One interpolation, at least one interpolation was required, right? Just one interpolation. The rest of it you could have guessed, right? Okay.
I appreciate that.
0.19, right?
0.19, yes.
What about between 0.18 and
0.17 and 0.2. Where is the 0.18? I don't see 0.18.
It's the third column from the right.
We are dealing with total temperature. This is a static temperature ratio, right? We are dealing with total temperatures. You don't see this pointer here. Let me see. I want to write on the screen. Let's see what happens.
Smart select.
We are dealing with these two numbers because we have calculated total, right? I don't want this anymore. Is this clear? Okay. So your Mach number is roughly, let's say it's 0.22, 0.22, which essentially means that you can have all of the other ratios as well, right? And you are also asked to find the total pressure loss between 0.1 and 0.2. So we are asked to find the PT2 divided by PT1, right? Total pressure loss. I mean, PT2 minus PT1, right? But what do we have here? We have PT2 divided by PT star, and also PT1 divided by PT star. We have these from the tables. So you plug those in, you can find this ratio. And using this ratio, you can find the PT2. You have this from here. PT1 is given to you is 100. Is it 100? I don't remember the number. 100 kilopascals. You can find PT2, and the difference between the two is going to be the total pressure drop. You're also asked to find the a static pressure drop, which is you have to use the same procedure to calculate the static pressure drop. The other part is asking you to find the enthalpy rise. The enthalpy rise, you have the enthalpy rise from 0.1 to the sonic condition, right? And you can also find the enthalpy rise from the 0.2 to the sonic condition. The enthalpy rise between 0.1 and 0.2, just going to be the subtraction between those two. Does this make sense? Is this clear? Yes?
How do we get that static condition again?
The static condition is going to be the exact same thing.
But are we given a static input? How do we calculate that?
You can actually go back to the okay, that's a very good question, because we are not given a static condition. How can we find the static condition, right? How can we find the static pressure drop? Think about it. I mean, like, this is a question for you guys.
Would we substitute velocity for Mach? And like the total equals static.
You don't need to use any equations. No equations.
What's the question again?
So Drew brought up a very important point, that we are not given any static pressures. We are only given the total pressures, right? How can we find the static pressure? One way to go about it is to use the equation, right? You have the Mach number, you should find the static temperature, and then find the speed of sound at that specific location, then find the velocity, then using that P is equals to a static total temperature is P plus your dynamic pressure, 1/2 rho V squared, right? So there are a lot of other variables that you need to calculate. But I'm asking about the other way.
Do we just assume it's at sea level?
Do we assume? No, you don't assume the number, no. How can you assume a number?
No, I said assume the total is equal to it.
No. The flow is moving, so you cannot make the assumption. They are definitely different.
Could you use the total pressure and then the star pressure ratio, and then given that with the Mach number, find the static pressure from the star pressure?
No. So we don't have the star pressure as well. But there is one thing we do have, and those are tables, right? What is the table we have here that you have forgotten about? It is the isentropic tables. What is the relationship between total conditions and static conditions? It's an isentropic process, so you can use the isentropic tables, right? And isentropic tables is going to give you what is the Mach number at the inlet is 0.2, right? It was 0.2, right? Come here, it's going to give you P divided by P star and PT divided by P. So total ratio between total temperature and the static pressure. You have PT, you have this ratio, you have the static pressure for both conditions. You can do this, right? As long as you have the Mach number. If you want to find the static value from the total value or the other way around, you have to go to the isentropic table. There are also equations out there you can use that they are in the lecture notes. I think we went over those equations as well, but you don't need to use them. It's going to be a lot of hassle. Okay. So hopefully, and what is next? I mean, we covered every part of it. And if you were to find these locations on the TS diagram, this is your TS diagram for a Rayleigh flow. We start from a Mach number smaller than 1, specifically 2.2. Then we increase it a little bit. It doesn't reach the sonic condition. So we are going to remain in this location. And this is going to represent your total heat input. How do you feel about this problem? So.
Need a few more examples.
There's just a lot.
I'm pretty sure if you solve the homework problem, you should get a hang of it, right? But the problem is, this is the easiest problem you will get from this. And this is subsonic problems. When you either reach choking or you don't reach the choking is going to be the easiest problem. Supersonic problems, when you reach choking, is actually a harder problem because you have to determine the location of a shock wave. It is on the homework, yeah. So I'm guessing we won't be able to get to it today, so I'll probably need to extend your homework or remove that problem from the homework. Probably do the second and just add it to homework 4, right? I know it is a little.
It's unfortunate. I spent 2 hours on that problem already.
You have already spent 2 hours on that problem? How did you spend 2 hours on it? We haven't gone over
Like 2 hours of staring at it, trying to figure it out. I see my notes. It's nothing happening because I'm like
10 minutes of
I'm missing something.
I'm like, I'm missing something. But he must have taught it. He went teach it the day before it's due. But that was wrong.
I mean, it is. Today it is not the day before it's due, is it?
Next class to do.
Yeah, well, you have a weekend in between.
Yeah, so today.
You have a whole weekend in between,
Like
right?
today's the last class before it's due.
Yeah.
Yeah, shoot, it is Wednesday, huh?
It is Wednesday, yeah. It is Wednesday.
Wait, is this homework? It's Tuesday.
No, it's a Monday.
But it's
Monday.
night.
Monday night. Alright, I can do that next class. But that's not enough time to do something.
We'll do all the other problems, except for
Just
that
make
one.
it different.
And then afterwards, you do it.
No, the last problem I'm just going to, so essentially you have to solve the first, is it 3 problems? First 3 problems, first 5 problems. You shouldn't solve you cannot, at this point you cannot solve the Fano problem, right? I mean, you can if you are creative enough, but I mean, I'm not creative enough, so myself, I wouldn't be able to solve it without going over the solutions. But you have the knowledge, that's the point.
Yeah, there's 5 problems.
So the first 4 problems, just solve the first 4 problems.
Number 4 is the one we haven't done yet.
Yeah, we just went over something like that in this class.
Number 4 is the shock location.
What is the number 5 then?
Number 5 is the turbine looking thingy with the mass flow rate, the exit Mach number.
I will go over the homework and send you an email. I guess that's the better way to go about it. Yeah. Yeah, that's a better plan. Yeah. Okay. So what do we want to do in the next 5 minutes?
goes, or something like problem 2 with the mock and lifting and drag? Or is it just a straight, like, because it's got the straight pressure difference? We use that across the whole plate.
Okay. Let's actually no and yes. Let's say, guys, let's say we have this flow that is going to hit this plate, right? How can I find the lift and drag? What is the definition of lift? For those of you who has passed aerodynamics here, let me see. I want to go one by one. This is very important. That's why I want to go one by one. What is who has passed aerodynamics? Show of hand. So you four have not passed aerodynamics. Fluids doesn't count. I mean, you have to read aerodynamics in your free time. I know they have given you the exemption, but that aerodynamics is a little different. Okay. So those of you who have passed aerodynamics, what is the definition of lift and drag?
It was an open book test.
What is the definition of lift and drag?
I would say the definition of lift is the force upwards on a body that makes it go up, which counters weight.
Is it force normal to the body?
No.
Force normal to what?
The angle of attack, yeah.
Force normal to what? Normal to the angle of attack? What does it even mean?
I mean, the lift is
To the core.
Upwards. That's normal to what?
The body, I would say.
Normal to the flow direction.
Yes.
Right? The normal force is the force that is normal to your body, right? To the core, right? So we have what about drag? Drag is going to be force tangential to the flow direction, right? In the direction of the flow, right? So lift, drag. What is the difference between lift per unit length and lift? Who remembers? It is in its name. It is lift per unit length. So a two-dimensional lift, which assume your depth is 1 meter or 1 feet, whatever, is lift per unit length. Lift per unit 1 length, right? So here, since it's a two-dimensional case, we are dealing with L prime and D prime, lift per unit length, drag per unit length, right? And what is the direction of pressure here?
Upwards. That way.
Pressure is always normal to your body. So pressure distribution is going to look like this. This is what you meant?
Yeah.
Okay.
He did point that way.
What's that?
I was thinking of,
He
like,
pointed.
I was thinking there's a vacuum up here, so the body's going that way.
Yeah. Okay, so to calculate your lift, you have to find, I'm assuming in that problem we don't have shear, right? Because we are not given any information about shear. To calculate lift, you have to find the normal component of pressure. How do we find the normal component of pressure? You have this angle. You can simply find the normal component as cosine and sine relationships. And for the drag, you have to find the tangential component of pressure. That's it. So you have to have the pressure distribution on this body to be able to find lift and drag, right? You can assume, I don't remember what was the exact problem, but if you have a shock wave, your pressure is going to be different, right, after the shock wave. And you also have to have the pressure distribution on top, right? Keep in mind that pressure is force per unit area. So to convert pressure to a force, you have to multiply it by your area. In this case, it's just going to be the length of this, whatever it is, right?
The pressure is constant after a shock wave, right?
That's the assumption. It is not a correct assumption, but that's the assumption. Yeah?
Got it.
So, pressure on top, pressure on the bottom minus the pressure on top, right? In the direction of normal to the flow is going to give you the lift. In the other direction is going to give you drag. This clear? Okay. I guess we can stop here.